Good morning. This is our narrated version of the PowerPoint for volcanic eruptions. So we always do volcanic eruptions after plate tectonics, and there's a reason for that. What kind of plate boundary you have or where your hot spot is sitting is a big control over whether or not you are going to have a shield volcano or a stratovolcano. So looking at the images here, the image on the left is a close-up view of a shield volcano. So look at the dark rock there. That's basalt. That's one clue that that's a shield volcano. Also notice that the person taking the picture is relatively close to the eruption. The image on the right, however, is much different, and that's a stratovolcano. Even with that pyroclastic cloud, I think you can still see the pointy shape of that mountain. That's a very famous volcanic eruption. Anybody want to take a guess on which one that might be? That is Mount St. Helens erupting on May 18th back in 1980. So we have talked about this material here in the past. I believe this was an extra credit question on maybe our second exam. This will be a 4-credit question on our third exam. So we don't have active volcanoes, melt, and igneous activity just anywhere. There are 3 basic settings under which this is going to happen. Number 1, divergent boundaries. In your oceanic settings, these are known as mid-ocean ridges, MORs, and spreading centers. But in the continental setting, they're known as rift zones. Don't forget that we have only one example of an active rift on this planet today, and that is the East African rift. How about a review question? Where can you give me an example of a failed rift? That answer is the Reelfoot Rift in New Madrid, Missouri. We'll learn more about that after the third exam when we talk about earthquakes. All right, our second setting are subduction zones. Remember that subduction zones are a type of convergent plate boundary. We had 2 types of subduction zones. We had ocean to continent and ocean to ocean. Don't forget, a good example of an ocean to continent subduction zone would be the Cascadia subduction zone in the Pacific Northwest. And a good example of an ocean-to-ocean subduction zone would be the Mariana Islands and Trench in the Western Pacific. All right, so our first 2 locations have to do with specific plate boundaries. I am going to remind you that not all plate boundaries produce igneous activity. Okay, so continent-to-continent collision and transform boundaries do not produce igneous activity. So the third location where you do have igneous activity, hotspots. These are mantle plumes. We discussed them in the plate tectonics unit. And don't forget the hotspots can be located in continental settings or oceanic settings. What's an example of a hotspot in a continental setting? As we discussed with plate tectonics, Yellowstone National Park. How about in an oceanic setting, Hawaii and Iceland? Here we are just looking at a drawing and an underwater photograph of pillow lava or pillow basalt. This is the shape of the basalt that you get at the surface there at a mid-ocean ridge axis. I think we might have looked at a slide similar to this back when we did our unit on igneous rocks. So these are both mafic lava flows. One is Pahoehoe, the ropey, which has slightly higher viscosity, and the other one is the Aa, which has a slightly lower viscosity and is therefore more chunky. Which of these lava flows is younger? The one on top, exactly. How do we know that? Well, 2 reasons. For one thing, it's so young, it's still molten. Look at all that orange. And the other reason is that it simply is flowing on top of the Pahoehoe, therefore the Pahoehoe must have been there first. So some of these slides I'm just going to skip over, and if you want to pause and read it, you can. But if there are slides that we were going to skip in class during a non-COVID semester, then we will just skip over them as well. But again, you can always pause this recording and read through them, or you can always go through the non-narrated PowerPoint. Okay, so we are going to discuss in class and in a video lesson that there are three types of volcanoes, but we will mostly focus on just two types of volcanoes for our third exam, shield volcanoes and stratovolcanoes. We're going to see that they're both very different from each other, and we will discuss the factors of what forms the different types of volcanoes, and we will also discuss how the stratovolcanoes are much more dangerous. Do you need to know everything on this slide? Yes, you do. All right, third bullet there. The type of volcano is dependent upon eruption style. We're going to see on an upcoming slide that we have pyroclastic eruptions and we have effusive eruptions. Now, what is eruption style dependent upon? This is a separate exam question here. Eruption style is dependent upon three things: magma type, viscosity, and volatile. So magma type, what we mean here, is it felsic, is it mafic, is it intermediate? Viscosity, is it high viscosity or low viscosity? Don't forget the viscosity refers to resistance to flow, and viscosity reflects silica content. Eruption style is also dependent upon volatiles. Volatiles are dissolved volcanic gases in the magma. Okay, so effusive eruptions. You do need to know the specifics about effusive eruptions versus pyroclastic eruptions. So effusive eruptions are relatively kind and gentle, and these are basically just going to produce lava flows. Okay, so eruptions of this type are going to produce basalt, meaning that you have mafic melt producing basalt like you would see in the active volcanoes on the Big Island of Hawaii. And what kind of volcano do effusive eruptions produce? They produce shield volcanoes. You don't need to worry about what's in parentheses there. We don't normally have time to discuss flood basalts in this particular class. Take a look at this. This is really cool. This is a shield volcano. All right, now you're right up on one of the vents of a shield volcano. It does look a little pointy, I will admit, but overall this volcano is relatively flat. This is a shield volcano, not a stratovolcano. So what kind of eruption is this? This is an effusive eruption. And what do you see besides the basalt in the background making the shield volcano? You see a lot of lava. Kind of makes sense. We might refer to that stuff there behind the helicopter as a lava fountain or lava curtain, and you see a lava flow there in the foreground, and it's somewhat of an optical illusion. So that helicopter can get really close to this eruption because this eruption is just not all that powerful. However, I don't think the helicopter is quite as close to the lava fountain as it looks. Okay, so I would say you could leave out the middle bullet here. So what are the specifics of our shield volcanoes? By the way, we will be drawing these volcanoes in class together and making big outlines with all the important aspects of each of the two major types of volcanoes. Shield volcanoes, they are huge. They tend to be the largest volcanoes on our planet, and they have broad, gentle slopes. They are not pointy. Do you need to know an example for your exam? Well, of course. So probably the easiest examples to remember are Mauna Loa, Mauna Kea, and Kilauea. These are the three most famous of the 5 active volcanoes that make up the Big Island of Hawaii. I think that's a typo, by the way. I think Haleakala is on a different island, and I never can remember the name of the 5th volcano. Just know one of these 3, Mauna Loa, Mauna Kea, or Kilauea. No, I don't count off for spelling on the exam. Now, that next to last bullet there is a potential extra credit question on your last exam. What is the name of the largest volcano in the solar system, and where is it located? Well, the name of that volcano is called Olympus Mons, and it is on Mars, not Earth. And it's a shield volcano, and it's extinct. extinct because all the volcanoes on Mars are extinct. So effusive eruptions, as we have mentioned before, well, they tend to be less hazardous to humans than the pyroclastic ones. We did look at this image before in class, for those of you that were in class, back when we did our unit on igneous rocks. And here we have two scientists walking away from a lava flow. No, they're not running for their lives. And they don't have to, and they know that. So this is part of an effusive eruption here. So this is a slowly creeping lava flow. Clearly this is quite recent. I mean, you see there, most of it is still molten. This is an image. I'm sure this is from Hawaii Volcanoes National Park, which is on the Big Island of Hawaii, and it's Kilauea Volcano. Anyway, you can let your tourists get really close to the lava flows here, and you see that with this picture. You see tourists over there in the top left, and they're just not very far from this brand new lava flow. Notice the dark rock. That's basalt, so this is definitely mafic melt, and it is a shield volcano. And this is the kind of volcano that you can live on, and you can put a national park on, and it's okay. I think this is a fun little image. I like to show this in class. I don't know if we'll have time in our COVID semester or not. But what you see here are some scientists on the Big Island of Hawaii. And here you've got a skylight. So what's beneath them is a lava tube, where lava underground is going to either create a new tube or follow existing tubes and spew that material offshore, making the Big Island even bigger. Okay, and how does a skylight form? Well, this is the scary part. A skylight forms when part of the roof over a lava tube caves in. And you see here a brave scientist right there at the edge trying to get a sample of that lava. Notice that crack just maybe 3 feet in front of their boots. So this is not necessarily the safest job on the planet. This photo appears to maybe be a little bit older, but kind of the same thing going on here. Is the scientist going to go take a sample? Perhaps, but what you're looking at here is a skylight. So this is a really good image because you can look down into that lava tube. By the way, on, I don't know if it's Oahu or Maui, it's one of those two islands that doesn't have the active volcanoes. The Thurston lava tubes are a place you can visit, and you can walk through the Thurston lava tubes on one of those other islands. And the reason you can do that is because the only volcanoes that are active are the ones on the Big Island. All those older islands to the northwest, the older island volcanoes are extinct. That's why it's safe to allow people to walk through the Thurston lava tubes. This lava tube here, you wouldn't walk through it. So here's an image of a lava fountain. I really like this image here. I may have showed you some of these images before when we did our unit on igneous rocks. And just look at the dark color of that lava. It reminds me of October leaves. Okay, so this is a pretty decent 3D drawing of how these big shield volcanoes can form islands over top of hot spots. Okay, so the Hawaiian Islands are where they exist in the middle of a plate where they don't belong. They exist there because of a mantle plume. So you see here the mantle plume, and you see that it's melting all the way through the plate. Now this is an oceanic plate, of course, it's the Pacific plate, and you can see the moho there pretty clearly. You see where you go from the crust to the lithospheric mantle. That's some review, by the way. And then the mantle plume is going to fuel the active volcanoes on the Big Island of Hawaii. And then of course you see a map there in the bottom right, and that has the correct list of the 5 active volcanoes on the Big Island of Hawaii. And then there's Loihi offshore. We'll talk about Loihi on an upcoming slide. In the background, you see an image of the very top of, that is either Mauna Loa or Mauna Kea. So these images are pretty good as well. This, I think, comes from a textbook that you guys haven't seen. Anyway, so let's start in the middle there. You have a nice drawing of the three biggest and most active volcanoes making up the Big Island: Mauna Loa, Mauna Kea, and Kilauea. Kilauea is the most active of all of them. Now you see there in the top right that even shield volcanoes can have craters and calderas. In class, we will discuss crater versus caldera. In the little inset drawing there, that's kind of neat because it shows how the structure of these big, broad shield volcanoes is built. And it has a lot to do with the low viscosity of this magma. Gases can easily escape. The magma can easily escape to the surface through multiple vents, fissures. So you have these smaller fissure eruptions, and you basically just build up this big, broad shield volcano over time. In the bottom left is a close-up of a fissure eruption. In the bottom right, that is an image of either Mauna Loa or Mauna Kea. And you see from a distance that indeed this volcano is not pointy. Your slopes are very gentle, maybe between 3 and 10 degrees. This is an image of Mauna Loa at night. This is an even better image of Mauna Loa at night because they're way far away. Taking this photograph. Now here's something interesting. You're looking at just the very top thin slice of that volcano. So these shield volcanoes are huge. And you know, as you're walking around the surface, you might be able to see the top of that volcano. And that might beg a question, where's the bottom of that volcano? And the answer is the bottom of that volcano is way down on the bottom of the Pacific Ocean floor. Shield volcanoes are indeed the largest volcanoes on this planet. This is an interesting slide, and I certainly recommend that you pause the slideshow and read through this. It's got a little bit of the history of Kilauea. So the Pu'uwa'u vent has been erupting continuously since 1983. Shows no signs of slowing down, and it has destroyed some neighborhoods. I think it's called Kalapani Gardens. That was, or Kalapana. That was a neighborhood that they built on the Big Island thinking that the lava would never go there. So what did the lava do? Well, of course, it went there and it took over and ruined a good part of that neighborhood. Okay, so now we're going to begin to discuss the second major type of volcano called the stratovolcano. In the bottom right corner, you see a beautiful picture there of a stratovolcano. Which one is that? I'm actually not sure. I just grabbed that image off the web. It looks a lot like Mount Fuji, but the rest of the background doesn't really look like Mount Fuji. Maybe that's somewhere in the Andes Mountains in South America. So what kind of eruption is going to produce a stratovolcano? And that answer is pyroclastic eruptions. Pyroclastic eruptions are the dangerous, explosive types of eruptions. They are going to produce the big, scary pyroclastic debris flows. That's that scary gray cloud that you see when these things erupt. They also will produce a lot of ash, ash falls, ash flows. You can have lava flows associated with your pyroclastic eruptions, and they tend to be andesitic or rhyolitic. But generally, the lava flows are probably part of a larger pyroclastic eruption, and you're not really even going to see those lava flows. What you're going to see, you know, hopefully from a distance or from a newscast, you're going to see the pyroclastic cloud. So these pyroclastic dangerous eruptions produce stratovolcanoes, which are our most dangerous volcanoes. Okay, a little more about stratovolcanoes. By the way, your textbook might also refer to these as composite volcanoes. Two words that mean basically the same thing. We are going to go with stratovolcanoes. So they are smaller than shield volcanoes, and they have the classic pointy volcano shape. So how does the structure of a stratovolcano build up? Well, it's going to consist of alternating layers of past lava flows and pyroclastic debris. Sometimes we can refer to pyroclastic debris as tephra, unconsolidated pyroclastic debris. And yes, these pyroclastic eruptions are very hazardous to humans. So your stratovolcanoes, if they are active or even dormant, people, scientists, need to keep an eye on that volcano, and we need to try and predict when it's going to erupt, because the only way you can save lives is to get people out of the way first. So here we're looking at a nice cross-section drawing of a stratovolcano. So notice the layers there. So those layers might kind of remind you of sedimentary rocks, but in this case, you know, the majority of that material is not sedimentary. So what you're going to have are just alternating layers of past eruptive material. And yeah, if you go long enough in between eruptions, you're going to have some weathering, and you might get some thin layers of sediments in between. But primarily, it's past eruption material deposited in discrete layers that's going to build up the cone shape of this volcano. Here's another image of basically the same thing. Okay, so some famous stratovolcanoes. Over on the left there, top left, that's Mount Fuji. And that is near Tokyo, I believe. I think it's Tokyo. Some parts of Tokyo, you can look out the window of your hotel and see beautiful Mount Fuji. Mount Etna is in the top right. Mount Etna is different. Okay, you might notice there's some darker colored rock, and it doesn't necessarily look so much like a big cone. Mount Etna is a very well-behaved stratovolcano that in a lot of ways it actually acts more like a shield volcano. The plate history there and the melt is very complicated. Okay, bottom left, that's a terrible image of Mount Kilimanjaro. That's taken with a satellite, and it just looks like it's kind of sunken in. But Mount Kilimanjaro is a pretty decent sized volcano in the East African Rift. Over on the right is Mount Rainier. How about a bigger image of Mount Rainier? Okay, so what city is that? That is Tacoma, Washington that we're looking at. So the person taking this picture is on the other side of Puget Sound, and they've turned around to look east. And then on the other side of the sound, you see Tacoma, Washington, and then you see mighty Mount Rainier in the background. So here's the interesting thing. We say that the stratovolcanoes are smaller than shield volcanoes, but they are not small. I have to admit that I would love to live in the Pacific Northwest. Anyway, but if you live in the Pacific Northwest, you have to understand, especially here in Tacoma, that Mount Rainier is an active and potentially very dangerous stratovolcano living just right outside your back door. And what do you see on top there? Snow and ice. What do you think happens to that snow and ice when you have a big hot eruption? It melts and creates something very dangerous that we refer to as a lahar. Okay, there's Mount Rainier again. Notice this time it looks a little smaller, so this city must be further away. And what city must this be? If you said Seattle, you're correct. There's the Space Needle over on the right. So Seattle is further away from Mount Rainier. Seattle is probably safe from pyroclastic flows and lahars. Seattle would certainly get the ash fall from a Mount Rainier eruption, and Seattle is also just kind of sitting there waiting on the next large subduction zone earthquake and tsunami. Mount St. Helens. I could talk about Mount St. Helens all day long. So this is a postcard perfect image of Mount St. Helens prior to May 18th, 1980. How do I know it was before that date? Because it looks like this in this picture. It doesn't look like that anymore. There's Spirit Lake, and there would be a crater at the top. You can't really see it from this vantage point. That's okay. And then you notice that it's covered with snow and ice. Now, what does Mount St. Helens look like now? Okay, before and after. So this is Mount St. Helens, what it looks like today. Okay, so you might notice that a good maybe 1/3 of the top of the mountain is gone. Okay, instead of having a crater, you now have this big, much larger, huge opening we refer to as a caldera. By the way, presence of a caldera is proof that a very large eruption happened in the past at this volcano. Of course, it was 1980, so we had lots of people witnessing, and we even had some photographs taken. Now you might notice in the center there is what looks like a little cone. That is something we refer to as the resurgent dome. And is Mount St. Helens still active? Very much so. And you see a small steam and ash eruption happening when they took this photo. And then there is Spirit Lake in the foreground. Well, I like to call it New Spirit Lake. A lot of the old Spirit Lake was filled in, but there's a lake there again, probably a different shape and not as big, and they just refer to it as Spirit Lake. So here we are comparing the sizes of your different volcanoes, okay? So Mount Rainier, which we just looked at, as big as it is, notice it's a heck of a lot smaller than Mauna Loa. So up there at the top, that's Mauna Loa, a huge shield volcano. So Mount Rainier is a lot smaller, but Mount Rainier is not small. And then the cinder cones we haven't discussed yet, but we will. And cinder cones, we're just going to make them an extra credit topic. But cinder cones are much, much smaller. So here you are looking at 3 different images, just kind of showing the different shapes, how they look. Okay, so on the top is, of course, that's Mauna Loa, big shield volcano. Bottom left, that's Lassen Peak. I'm sorry, no, that's Mount Shasta, but also in California, as Lassen Peak is. Anyway, so Northern California is part of the Cascadia subduction zone. So some of these active volcanoes in the Cascades are in Northern California. And then on the bottom right, that's SP crater, which is out in Arizona. I've been to that crater. We climbed to the top of that crater. It was really fun. Okay, volcano structure. If there's time, we will attempt to draw something on the board from this. So, you know, what's feeding the volcano is the magma chamber. And then you have the volcanic neck, sometimes referred to as the volcanic pipe. It's basically your conduit for eruptive material to make its way out of the volcano. The sides are referred to as flanks, like the flanks of horses. And then at the top, you have a crater, which it is going to be a downdropped area, kind of like a bowl shape. The crater is simply the summit vent. And we are going to focus on stratovolcanoes here when we talk about volcano structure. Okay, just for fun, this is a famous place in Wyoming. It's called Devil's Tower, and it's basalt, columnar basalt, and scientists think it's probably an exposed volcanic neck. I've been to Devil's Tower. It's really, really cool. This is Shiprock, New Mexico. This is another exposed volcanic neck. I haven't been to this one, but and it looks really cool, but I don't think it's as cool as Devil's Tower. This is just a little drawing trying to show how a volcanic neck forms. Of course, this is after the volcano has gone extinct, and then the material that made up the flanks is a little bit easier to erode, so it erodes away and leaves behind what was in the volcanic neck long ago. Columnar basalt is a lot of fun. We really won't take any time for it. But I'll just kind of call your attention to, if you look there in the center B, you see that basically these things tend to have 5 sides. So sometimes basalt will look like it's in columns, like you see over there on the left, or like you might see at Devil's Tower, Wyoming. And this just has to do with that basalt cooling and contracting. And then over on the right, of course, that is pillow lava, pillow basalt, like you might typically see at a mid-ocean ridge. All right, what's the difference between a crater and a caldera? We will discuss this in class together. So then I suppose it'll be in a video lesson. I'm going to film video lessons on Wednesday of this week in the afternoon. Okay, so a crater is the summit vent. And both shield volcanoes and stratovolcanoes can have craters, although in the case of a stratovolcano, those craters tend to be a little more deep. And they form as eruptive material accumulates around the central vent after you have many eruptions over time. Now, craters are big. They can easily be half a kilometer across and easily at least a couple hundred meters deep. But calderas are going to be much bigger features. Okay, so we expect all volcanoes to have a crater, and a few of them will have a caldera instead. And they don't all have calderas. Why? Because calderas are only going to develop after you've had some kind of major eruption, pretty much emptying the magma chamber and then causing the center of that volcano to collapse into the emptying magma chamber. And this creates a very large feature. Okay, so they can be thousands of meters across and several hundred meters deep. And of course, a great example of a caldera is the caldera that is now at Mount St. Helens. So this is a neat satellite image. This is a very famous volcano, Vesuvius in Italy. And you see a crater there. And notice the kind of pink reddish material around the crater. This reminds us that this is a felsic volcano, a stratovolcano, very dangerous. And what is that lighter colored material surrounding Vesuvius? Well, that's a big city. Naples, I believe Naples is the modern city that surrounds Vesuvius. And Vesuvius is famous because of Pompeii. The cities of Pompeii and Herculaneum were wiped out and buried in ash during a Vesuvius eruption back in 79 AD. Those towns were buried in ash, and they weren't discovered again by modern humans until I believe it was in the 1700s that they accidentally excavated part of Pompeii. And then, of course, you know, they brought in archaeologists and they continued to dig, and now Pompeii is a tourist destination. I don't know if Herculaneum is or not. Now, Tambora in Indonesia, this is a very famous volcano. When did Tambora erupt? I think it was about 1816. Is that right? Maybe 1815. It erupted in 1816, was a year without a summer. So Tambora is a very famous stratovolcano in Indonesia. And it's had very large eruptions in the past, and this image is zooming into the caldera, and then in the middle, that thing that looks like a raised bump, well, that is the resurgent dome, just like Mount St. Helens has. Okay, so this is a different volcano in Indonesia, but what I like to ask people in class, if we have time to look at this, is how many craters do you see? So you clearly see that first one there that has the pretty blue water in it and the sunshine on it. But there's another crater over there. And you see water in that one as well. It's just that the sun isn't shining over there quite yet, so it looks kind of in shadow. And I just recently learned from some image I saw pop up on my computer, there's actually a third crater here. Now, if they were taking this image with a drone camera directly overhead, you would see the third crater, but there's a third crater over there kind of to the top right. Here's a volcanic crater in New Zealand, and you might notice that they are down within the crater, taking this image, and it is open to water. So this is one that's right on the edge of an island, or this crater is part of what makes up that island. And I might ask, is this thing still active? Indeed it is. Okay, that's not fog, that is steam. This is an active volcano. This is Diamond Head Crater in Oahu, and this is very famous. So this is Hawaiian Islands, so these are shield volcanoes. Now Oahu, the volcanoes on Oahu are extinct because Oahu has moved off of the hotspot. And you'll notice that this crater looks a lot different than the crater for a stratovolcano. That's because this is a shield volcano. This crater is also rather old and has eroded a good bit, and if you look carefully, you're going to see some buildings in that crater. And you can put buildings in the crater. You can let people live in there if they wanted to, because you know that volcano is extinct. Okay, so how does a caldera form? So this is a nice step-by-step drawing showing how that might happen, and we could pretend that this is, say, Mount St. Helens. So in the top image there, you have your bloated magma chamber, and something happens that releases the pressure, the gases come out of solution, and now, kaboom, you're having your pyroclastic eruption. Okay, so there in time 2, the image in the middle, labeled B, you've lost some of that material, so the magma chamber is starting to deflate, and you're starting to form normal faults, and you're starting to have that volcano collapse inwards. And then on the bottom image, at time C, your eruption is over, and the magma chamber has at least somewhat emptied, and it no longer could support the weight of the volcano on top. So you have basically the center of that stratovolcano collapse down into the emptied magma chamber, and that is what makes a caldera. Don't forget that Yellowstone National Park is a caldera. Speaking of Yellowstone, okay, so in the top image there, in the green is the outline of Yellowstone National Park. The black dashed line is the outline of the caldera. Okay, so almost half of that park is taken up by the caldera. This caldera is huge, all right, and it was 640,000 years ago that we last had an eruption here at Yellowstone that created that present caldera that is within the park. And that was a big eruption. And how do we know? Lots of reasons, including the size of that caldera, but also mapping the ash beds, and that's what you see in the image there towards the bottom. Okay, so they have 3 relatively recent ash beds mapped out. So the Huckleberry Ridge in the dark yellow, 2.1 million years ago, and the ash fallout covered several states. And then a little more recently, you had the Mesa Falls eruption 1.3 million years ago, and you see there that the ash covered a smaller region, yet still big. And then you see the most recent super eruption 640,000 years ago. The Lava Creek ash bed covered many states. So of these 3 recent eruptions, the one that was the biggest was the one that was the most recent. And then go up to Mount St. Helens there and look at that little tiny ash. Now, at the time in 1980, that was a big deal. 57 people got killed. We had ash falling that went all across to the east, crossed Washington State and into Idaho. But boy, Mount St. Helens was nothing compared to what a Yellowstone eruption can do. So here's another good drawing or set of images to show how a caldera forms, and in this case we're looking at Crater Lake, Oregon. So up there at the top, that's time 1, and that was Mount Mazama. What's it been, 7,000 to 10,000 years ago, I think, when Mount Mazama erupted, and you had your huge bloated magma chamber. Your eruption begins, and your eruption's going on for many hours, and you're starting to deflate the magma chamber. And then in the third image there, you have partially emptied that magma chamber, and you've now had the volcano structure collapse down in it and form this very big depression called a caldera. And then the image at the bottom is what it looks like today. So you have a resurgent dome there poking up out of the water. And why do you have water? It's Pacific Northwest. You have plenty of rainfall, so that caldera is going to fill up with water and form a lake. Okay, so here's that image of Mount St. Helens again, and just to remind you guys, Mount St. Helens has a caldera, not a crater, but a caldera because it had a huge eruption back in 1980, and it has a resurgent dome there in the center because it's still active, and new small eruptions over time It's trying to rebuild itself to its former glory. Okay, so this is another little step-by-step here on how do you go from Mount Mazama to Crater Lake. Okay, so this caldera here on what was Mount Mazama, now it's a caldera. It's called Crater Lake, but it's a caldera. I think they should change the name to Caldera Lake. And then there's Wizard Island. This is probably my favorite image of Crater Lake, Oregon. Hey, by the way, that's an extra credit question. Is Crater Lake, Oregon really a crater? No, it's a caldera. What is Wizard Island? It's a resurgent dome. They say this lake's really deep. I've never been there. I'd really like to go there sometime. I want to swim in it, or at least put a kayak in it. Okay, cinder cones. So cinder cones are just for fun, and they're just going to be basically an extra credit question. I think I might ask you to give me an example of a cinder cone. So when we have a normal class and we get to, hang out together several times a week, we do take some time to look at cinder cones. So we'll just briefly discuss them here. So there is a third type of volcano called a cinder cone. They're much, much smaller than your stratovolcanoes. And why is it called a cinder cone? Because it's a cone-shaped pile of tephra. Remember, tephra is a generic term for unconsolidated volcanic debris. These things tend to be almost perfectly symmetrical, and they're very steep, 40 degrees, and usually they have a crater at the summit. They tend to be made of basalt. They tend to occur in groups. You see a bunch of them out in the western United States. Say if you fly into Vegas and then you head east and start going to the national parks in Utah and Arizona, you're going to see a bunch of cinder cones. And they have wicked short lifespans. So the actual name of this cinder cone, it's called Ship Pot Crater. You may call it SP Crater for short. That's usually what the textbooks do. This is a great example of a cinder cone that you might use for that extra credit question on the third exam. Notice how perfectly symmetrical it is. Notice the dark material. It's basalt. So this is near Sunset Craters National Park in Arizona. Back in the Maymester of 2012, there was a group of us that took a small group, a couple of us professors that took a small group of students on a field trip class out west, and we saw a lot of amazing things, but I think this might have been my favorite because I'd never seen a volcano before. We climbed to the top of it, and it took a while. It took me a good 45 minutes, and some of the younger folks could scramble up quicker, and some of the students it took them longer. It just depended on, your climbing abilities, but it wasn't hard climbing, and you didn't need ropes or equipment. And you get up to the top. Of course, we brought lunch and water, and we brought our field notebooks and cameras, and we took a lot of pictures, and we talked about the geology of the area, and we had lunch, and we hung out there for quite a while. And you cannot see down to the bottom of the crater in this image. You cannot see down to the bottom of the crater if you go there in person, because the crater is deep. It's that deep, and you can only get so close to the edge. So us professors weren't going to let students get too close to the edge anyway. And even before we could tell them to come on back where it was safe, they would start to hear the rattles of the rattlesnakes. So the rattlesnakes hung out on the steep parts of the crater, and that was a perfect place for them, because if students got too close to the crater where they could fall in and get hurt pretty badly, well, they wouldn't go any further once they heard the rattlesnakes. Here's just another image of a cinder cone. I don't know if this one has a particular name or not, but this is in the Mojave National Preserve in California. And here's a couple more images of that SP crater. Okay, Paracutin in Mexico. This is a neat little story, and I love to talk about it in class. I don't know if we'll have time or not this semester. Probably not. Paracutin is another example of a famous cinder cone, and it's so famous that it has its own little corner in the National History Museum of the Smithsonian in DC. So the Natural History Museum is the Science Museum, and this little corner is dedicated to Paracutin. So 1944, World War II was going on, and in this farm field in Mexico, Central America, you started getting earthquakes where they hadn't previously had, earthquakes that they definitely could feel. So that went on for a couple of weeks, and then on February 20th, they started to see cracks in the ground, and hot rocks were coming out of the cracks, and gases. As you can imagine, they might have thought that the world was coming to an end. What was really happening is that a volcano was growing right there in front of their eyes. On the first day, it grew 130 feet. Imagine sitting there watching that. Although maybe people were scared and just ran away. On the fifth day, or by the fifth day, it had reached 330 feet. So within a year, most of that eruptive material had escaped. And it had a lifespan of 9 years. So after 9 years of intermittent eruptions and continuous lava flows, it stopped, and that was it. It was extinct. So when we say these volcanoes have short lifespans, we really mean it. So here's an image from June of 1944. And you see Paracutin there in the background, having it just continuing to erupt. That particular type of basalt there, we would refer to that as like you might find on the Big Island of Hawaii. And here it's 30 feet thick, and you see that that appears to be a church. And really the only thing from the church that isn't covered by the lava flow is the top spires. And it covered most of this particular village, and those people had to just move away and start over somewhere new. So there's an image of Paracutin on the left, and there's an image of that nearly buried church in that village nearby. Okay, so fissure eruptions, we don't really have time for this, but I will just point out those last couple bullets there. This is not on your exam, but flood basalts do exist from time to time. We don't have any flood basalts currently going on this planet right now to tell you about, but there's a couple of flood basalts from the past that are very famous. So about 250 million years ago, at the end of the Permian, we had the Permian extinction. It was the worst mass extinction this planet had ever seen. And we're pretty sure that the dominant cause of this were flood basalts that happened in what is today Siberia, or part of Russia, over on the Eurasian plate. And then it happened again 65 million years ago in what is today India. They refer to that as the Deccan Traps. And so as we discussed before, we had the meteorite impact at Chicxulub, which is down there in Mexico, Central America, just offshore. But it wasn't just the meteorite impact. We were also having these flood basalts, large outpourings of salt in what was then India. And these two things combined changed the climate enough that the dinosaurs went extinct. Here are just some images of fissure eruptions. Here's another image. I like the drawing up on the top left, just showing this low viscosity mafic magma that can easily escape to the surface at many different openings, creating fissure eruptions, and this can help lead to flood basalts. But again, we don't have any current flood basalts happening on this planet. Maybe that's a good thing. Okay, more on eruption style. If we were in class, I would have you write down bullets 1, 3, and 4. Okay, that first bullet we mentioned early on in this discussion, eruption style, depends upon magma type, viscosity, and volatiles. And then we had 3 different magma types, felsic, intermediate, and mafic. Well, 3 that erupt. Ultramafic does not erupt today anymore. Okay, magma type reflects silica content. Okay, so we're going to see that the higher the silica content, the higher the viscosity, and therefore the more dangerous the volcano. And another way to think about it is this. Remember that felsic magma might produce granite or rhyolite, felsic minerals. Your felsic magma has a high silica content. So the more felsic the magma, the higher the silica content, the more dangerous the volcano, like a Mount St. Helens type of volcano. Okay, more on eruption style. What would I have you write down? I would write down the last two bullets. We'll discuss all of them, but the last two bullets you should definitely highlight or write down. Right, so felsic magma has a higher silica content, mafic magma has a lower silica content, and intermediate magma has kind of an in-between silica content. Don't forget that both felsic magma and intermediate magma give us the stratovolcanoes, which are dangerous. And the mafic magma gives us the shield volcanoes, which are not so bad. So silica content affects viscosity. Don't forget that viscosity refers to resistance to flow. And a magma with a high viscosity has a high resistance to flow. And that means it has a high silica content, and that means it's very dangerous. Okay, so important bullet here, that last bullet. Higher silica content gives us higher viscosity and a more dangerous volcano. And then, of course, vice versa, the opposite is true. If you had a lower silica content, that would give you lower viscosity, and that would give you perhaps effusive eruptions and a shield volcano. You can skip this slide here. You can skip this slide, or you can pause here and take a look at it. I guess one thing I might point out on this slide that we haven't talked about yet, but will soon, is temperature. You're going to see that your mafic magma, which fuels your gentle shield volcanoes, is going to have a higher temperature than your felsic magma. Okay, viscosity. Really, every bullet here is important. So we have discussed viscosity before. We talked about it back when we did our unit on igneous rocks. What does it refer to? Resistance to flow. What does it reflect? Silica content. So higher viscosity, higher silica content is going to give you more felsic magma and give you dangerous volcanoes like your stratovolcanoes. Lower viscosity associated with a lower silica content will give you more mafic magma and will give you, say, effusive eruptions and build shield volcanoes. Now, that last bullet there is important, and it's a separate exam question. What does viscosity depend upon? Okay, so viscosity depends upon three things. It depends upon silica content, temperature, and volatiles. And in class, we are going to build an outline comparing stratovolcanoes and shield volcanoes and every aspect of them, including things like viscosity, silica content, temperature, and volatiles. So as we have mentioned before, the higher the silica content, the higher the viscosity. The lower the silica content, the lower the viscosity. How about temperature? We haven't talked about that yet. But well, let me ask you guys, and we usually talk about this in class, but probably won't this semester. If you had 2 plates of French toast and you have 2 glass bottles of real maple syrup. No, it's not that fake log cabin stuff. It's the real syrup. It's $6 a bottle, but it's worth it. Anyway, you got 2 of these glass bottles. One is in the cabinet, one is in the refrigerator. Okay, so you're going to take the bottle out of the refrigerator and set it on the stove. You're going to take the bottle of syrup out of the cabinet, and you're going to loosen the lid and put it in the microwave, maybe just 30 seconds. You want to heat it up a little bit. And then you're going to take your 2 stacks of French toast, and you're going to take your 2 bottles of syrup. You take the lid off both of them. They're both full and brand new. One is cold syrup, one is warm syrup. And then when you go to pour them on the 2 stacks of French toast, you're going to hold them at the same angle. So you want everything to be the same except the temperature. So which syrup is going to flow faster, easier, and further? The warm syrup or the cold syrup? You guessed it, the warm syrup is going to flow better. Okay, therefore a higher temperature magma leads to lower viscosity and effusive eruptions, whereas a lower temperature magma leads to higher viscosity and pyroclastic eruptions. And then volatiles. Well, we'll get to the volatiles soon. You can skip this one, or you can pause and read it. Same thing here. You can skip this slide or pause and read it. Same thing here. You can skip this slide or pause and read it. Okay, so we do need to discuss the gases. I think we'll do that briefly here. So the gases are complicated. All magmas are going to have some volatiles, some volcanic gases. Some magmas will have more, some magmas will have less. So the presence of gases will actually reduce the viscosity a little bit. Therefore, it might sound like gases are good, but the bad outweighs the good. The presence of gases can lead to a dangerous buildup of gas pressure in the magma chamber. But let's take a look at these two images. So the image on the top left is a zoomed in look at Mount St. Helens. You're in the caldera, there is the resurgent dome, and it's having an eruption trying to rebuild itself to its former glory. All right, so, and that's associated with the high silica felsic magma. Okay, it's also a low temperature magma, and you have a high viscosity. Therefore, the gases do not easily escape, so you get a dangerous buildup of gas pressure in the magma chamber, which is eventually going to lead to a pyroclastic eruption. Okay, now let's look across the bottom here. So that image on the bottom right is a shield volcano, of course. Look at the dark colored rock, the basalt, the nice gentle lava flows there. That is a low silica magma that has a low viscosity. It's also a high temperature magma, which helps it to have a low viscosity, and the gases can escape. And you don't really have this material necessarily hanging out in one discrete magma chamber. It's easily making its way to the surface at many different openings that we refer to as fissures. Okay, so here this set of drawings is pretty good. We're trying to show how the presence of silica is going to affect viscosity and eruption style. On the left, so each of those tan triangles is going to represent a silica tetrahedra. Remember the silica tetrahedra? That goes way back to the beginning of the semester and talking about minerals. So the more of those silica tetrahedra that you have, as in a high silica magma, it also has lower temperature and therefore higher viscosity, meaning it does not flow easily. So what happens is that the magma cannot easily make its way to the surface, and the gases cannot easily escape. So you end up with this bloated magma chamber with all these dissolved gases in it, and that's like a ticking time bomb. And we'll talk about that more on an upcoming slide. I think this is going to be another 2-hour PowerPoint, by the way. And that's fueling your stratovolcano over there on the left. Okay, now let's look at everything on the right. Notice you have fewer of those triangles. So this is representing a lower silica magma, which also has a higher temperature, therefore a lower viscosity. So this material flows easily. So the magma can easily escape to the surface in many different openings called fissures. Also, the gases can easily escape. So you don't necessarily have this discrete magma chamber. So you're going to have these gentle effusive lava flows that are going to build up this big, broad shield volcano like you see there at the top on the right. Okay, volatiles. Let's write down, how about bullets 1 and 4? The first and the last bullet. Those are very important. Okay, so we're going to learn what the volatiles are, the different gases. So volatiles, that term basically just refers to substances that easily exist as gases at Earth's surface, meaning at the kind of low pressures that you have at Earth's surface. So volcanic gases are going to be present in the magma. Some magmas have more volatiles, some magmas have less. So as I may have mentioned on an earlier slide, you know, it sounds like volcanic gases are good because they reduce viscosity, but they're actually bad. And the bad outweighs the good because the volatiles can lead to a dangerous buildup of gas pressure in the magma chamber. Bottom line, that last bullet there, the more felsic the magma, the higher the volatile content. And again, the presence of many volatiles is potentially quite dangerous. Volcanic gases, are you going to need to know these for your first exam? I'm sorry, for your third exam? Yes. It'll be multiple choice. Water, H2O. Water vapor, of course, we mean in the gas form. It's the most abundant volatile. But then there's also carbon dioxide and sulfur dioxide. So SO2, sulfur dioxide, this is responsible for Yellowstone National Park smelling like rotten eggs. So as you walk around the park, it smells like that constantly. And I'm sure some of the visitors think it's yucky. I thought it was really cool when I was there because the whole time you're walking around looking at this beautiful, magnificent place, I just can't believe this is in our country. How awesome is this? But you know what? There's a dark side to it too. It's a very active supervolcano, and because you smell that sulfur dioxide gas, it kind of reminds you that it's a dangerous place. But then there's also hydrogen sulfide. So later in this PowerPoint, we're going to discuss how the gases alone can cause tragedy, even if you don't have an eruption. Okay, so volcanic gases, how do they affect eruption style? Okay, if you just write down the first bullet here, I think that would be okay. So anyway, so magma that has a high volatile content, like you might get with a felsic magma, silica-rich magma, this is eventually going to lead to pyroclastic eruptions, the big scary gray cloud type of eruptions like we saw with Mount St. Helens back in 1980. So we're going to go through some of the steps on how that happens and why or how these volcanic gases can lead to big scary eruptions. So as you have more magma, say rising up from that subduction zone, entering the magma chamber, it's going to exert more pressure on the walls of the magma chamber. And if you have these volatiles, dissolved gases in the magma, well, that's going to add to that pressure. Let's write down all three bullets here. This is important stuff. Okay, so what's dangerous about this? So as you get more magma with dissolved gases in it entering that magma chamber, eventually that magma chamber is going to get pretty darn full, okay? And you've just got this huge buildup of pressure, including gas pressure, inside that magma chamber. So what's going to happen is this is going to push outwards on the rocks surrounding the magma chamber, and you're going to cause fractures. You're going to cause big cracks in the volcano. You're going to weaken the flanks of the volcano. Okay, so you're always going to have some kind of blockage in that volcanic conduit, that volcanic neck. And what the blockage does is it keeps these gases under pressure. Okay, so as long as that volcano is kept under pressure, the gases remain dissolved. So gases are easily compressed. Liquids not so much, but gases are. So this is very much like dissolved carbon dioxide in a can of soda. All right, or better yet, let's imagine a clear glass bottle of soda. Whatever your favorite soda is. If I had to choose a favorite soda, I guess I'd have to choose Dr. Pepper. I don't really drink soda anymore because it's just so bad for you. But yeah, I do kind of miss Dr. Pepper. So you got your glass bottle of soda, and you haven't opened the top yet. And when you buy it, it looks kind of flat. If you kind of move the bottle around, you see the liquid moving. Do you see any bubbles yet? And the answer is no, you do not. Because when they are bottling this Dr. Pepper at the bottling plant, somewhere in North Carolina perhaps, they're bottling it under pressure. So the CO2 is dissolved, compressed in that liquid. So what do you have to do to see the bubbles in your bottle of Dr. Pepper? Well, the answer is simply just open it. Just pop the top. That's all it takes. You pop the top. Now, so you hear that little sound. that it makes, and then all of a sudden you see all those frothy bubbles of CO2 that seem to make that soda taste even better. Well, the volcano is very similar, except in a very dangerous way. So think about if you were to shake that bottle of soda, either on purpose to do an experiment or simply that you were driving and it fell onto the floor of your car and it rolled around a little bit, and then you got home and you took that bottle of soda to the kitchen and you forgot for a second that it hit the floor, so you go ahead and open it and it's been shaken up. What happens is it's going to like kind of spew all over the place. Well, it's going to be similar with our volcanic eruptions. So that third bullet's pretty important. Anything that releases the gas pressure, in other words, something that might open the conduit, something that might release the blockage of the conduit. This could be fractures on the sides of the volcano, earthquakes, landslides. Anything that releases that pressure causes those gases to come out of solution and pop up into a gas form. So they expand. Therefore, the volume of the magma in that chamber is going to expand. But you have limited space in that magma chamber, so there's nowhere for this material to go other than up and out of the volcano in a dangerous, explosive eruption. Okay, so again, exactly like what happens if you were to shake a can of soda and then pop the top. The gases expand rapidly, the magma, the volume of the magma itself expands. It forces its way out of the volcano in a very violent, life-threatening manner, and we call this a pyroclastic eruption. And this is the kind of eruption that you need to try to predict so that you can evacuate people out of the area before it erupts. So this is a neat slide to show that. Now, to be fair, I wish they had used a clear bottle, either plastic or glass. They didn't. That's okay. We kind of still see what's going on. I think it's a generic cola, of course. So they shook it, didn't they, before they opened it? Yeah. So over on the left, the two round bubbles there are pretty good drawings to show what's happening in the magma chamber. On the left, it just looks orange. You don't really see any gases. They are there, but they are compressed and dissolved or in solution in the magma. And then that bubble further to the top right, where you now see all the bubbles, that's what it looks like after the pressure's been released. It's like that bottle of soda, and now bam, all these gases pop up in the gas form, and you have the volume expanding and nowhere for it to go but blow out the top of that volcano. Okay, so Mount St. Helens. We will discuss Mount St. Helens. What's on this slide you will not need to know for your exam. You will on one of the upcoming slides. I'll let you know when we get there. For now, let's just listen to the background. So Mount St. Helens is a very active volcano. It's the most active volcano in all of the Cascades. However, for 123 years prior to 1980, it had been relatively quiet. Okay, is 123 years long enough for people to become complacent and think that their volcano is not dangerous? Well, yes, that's plenty long enough time for humans to become complacent. In March of 1980, it began to show signs of unrest, such as what? Numerous, relatively strong, shallow earthquakes were being recorded. That was very concerning. There were also steam and ash eruptions taking place at the summit. That was concerning. There were new fractures, cracks forming around the summit. This also on this slide is not on your exam. I think the most scary thing that was happening is that there was a bulge growing on the north flank of the volcano, meaning that the land was kind of pushing outward. The side of the volcano was pushing outward. What's going to make that happen? Well, magma, of course. Okay, so I would find that very disturbing. So they declared danger zones and hazard maps surrounding Mount St. Helens. They knew it was going to erupt, but you know, it's really hard to say exactly when, exactly which day and which time is it going to erupt. So they evacuated people because that was the right thing to do. You can't just let them live there and then die horrible deaths when the volcano erupts, even if they are bitching at you and whining to go back home because they never want to listen to the scientists, kind of like what's going on with this virus. But anyway, they should have listened to the scientists in both of those cases. Here is an image of Mount St. Helens before the eruption, perhaps many days or a month or two before the eruption, and you see there's a helicopter there that's going to go fly over the crater and take some readings, and then you see a scientist standing there with a machine, and he's going to take some readings. Maybe he can get gas readings from that far away. Maybe look at some temperature changes on the rocks of the flanks. Trying to study it safely from a distance. Would that be a safe enough distance if it erupted right now? No. Okay, you need to write this down. All of it. All right, so Mount St. Helens erupted. It was May 18th, 1980, 8:32 a.m., a Sunday morning. No, you don't need to know the time of the day of the week. But I'll let you know this for a reason. Okay, so here's the scary thing. The Saturday before it erupted, one day before, officials grew sick and tired of listening to the residents whine about, I need to go back and get my snowmobiles because I sell snowmobiles. I need to get my inventory. I have a herd of cattle and I need to go feed them. I want to go back home and check on things and water the plants or whatever. So Saturday, they had opened up the danger zone for several hours to let people back in to do what they needed to do, and then they had to leave again. Well, they had another one scheduled for Sunday, and luckily it wasn't scheduled until a little later in the day. I don't know if that was just dumb luck or if they did that because maybe a lot of people were going to church, but they didn't let them in this early in the morning, and that was a good thing because before they opened it up on Sunday, the eruption happened. So you're going to need to know the 4 things that were true about the eruption on that day. 3 of them are on this slide. The 4th one will be on the next slide. Okay, so the first thing that happened is you had a magnitude 5.8 shallow earthquake. Okay, and that of course was caused by magma shifting in the magma chamber. So that's a big quake, and it shook the mountain. All right, and then what happened next is that, remember that north flank had a bulge on it. And how do you change the shape of rock in the brittle realm? And the answer is you do that by causing fractures. So that bulge, that side of the mountain was all fractured up. It was very weak. So all it took was this, 5.1 earthquake, and the north flank of the mountain slid away. It was the largest landslide in recorded history. So that was the equivalent of shaking your soda and popping the top. Okay, so the pressure inside the magma chamber was released. Those gases popped out of solution into a gas form. The volume of the magma increased, and kaboom! Now your pyroclastic eruption begins. Okay, this is a continuation of the last slide and also on your exam. By the way, short answer question here. What was the eruption sequence on the morning that Mount St. Helens erupted? Okay, so we had two aspects to this pyroclastic blast. You had a vertical out the summit, the crater, as you expect with all of these pyroclastic eruptions, but you also had a lateral blast out the north flank that just kind of like hung close to the ground. And that happened because you lost the north flank of the mountain. And that lateral blast is part of the reason why there were 57 people killed in that eruption. There were people that otherwise would have been in a safe enough area, but because the north flank of the mountain blew away, they were not in a safe area. And the 4th thing that happened is that last bullet there, a lahar. So remember the pictures of Mount St. Helens before? The snow and ice on top, how pretty it was? Okay, well what happens when you have a big pyroclastic eruption and you release a lot of heat is that you melt all that snow and ice, and it makes something called a lahar. A lahar is a volcanic debris flow, and it is super dangerous. You can't outrun it. If you're in its path, you can't outswim it. So the lahar accompanied the pyroclastic flow, and it basically raced down the sides of the mountain, and then it left the mountain and followed river and stream channels, sometimes tens of kilometers distance away from the volcano. This is a real nice before and after image of Mount St. Helens. Mount St. Helens before on the left, perfect looking, beautiful volcanic mountain and Spirit Lake, and then boy, look at it there on the right. And this image on the right would have been very soon after the eruption ended. Maybe not, I mean, it went on for many hours, not quite 24 hours, not quite a full day. So maybe it was a few days later when they decided they could venture in and take some photos. But you see most of Spirit Lake's been filled in. You see that you've lost 1,350 feet of the mountain. You've lost that bulging north flank. And you're looking now into, how can you see into that caldera? Very easily, because you're looking from the north, where the north flank kind of disappeared. This is scary. I love showing this image in class. So this is a river. I don't know which one. Perhaps North Fork of the Toutle River. So you see all those trees in the river because they were knocked down by the blast and then caught up in the lahar, and they're in the river. You see a person for scale walking on the other riverbank there. And then the arrows are pointing. You see how far up on those trees you have that muddy material. That shows you how tall the lahar was. Now look at the person for scale. So that lahar would have been many, many, many feet up above their head. If there were people on the banks of this river when that lahar hit, well, they were definitely killed. What we're looking at here is it going to tell us? Okay, August of 1980. So a couple, 3 months later, Mount St. Helens is having a much smaller eruption. And here's an image of it. Okay, so what I have never been able to find online or at the USGS website or anywhere, I've never been able to find a hazard map for Mount St. Helens. There are reasons for it, but we just don't have time for it this semester. What I can show you is a typical hazard map for Mount Rainier. I like to show this in class, and we may or may not have time for it. We'll see. Anyway, so Mount Rainier, all right, what are we looking at here? Okay, in the dark gray there, that's the area of the mountain that will be affected by lava flows and pyroclastic flows. Nobody would live through that. Okay, so then the other colors are lahars. So in red, small lahars, recurrence interval less than 100 years. They go out onto the mountains and streams and only travel so far. And the orange, moderate lahars with recurrence intervals 100 to 500 years. And they go out a good bit further on those rivers and streams. A lot further in some cases. And then in yellow, large lahars with recurrence intervals of 500 to 1,000 years. And they go out pretty far on the rivers and streams. So what I'm going to point out here are that there are plenty of towns that are sitting on these rivers, and the towns themselves are built on past lahar debris. Okay, so Orting, up there in the orange, getting close to Puyallup, is a town called Orting. And I saw something on a Discovery Channel years ago. The public schools there in that town, yes, they have fire drills, as we're going to have everywhere. You know, we have tornado drills. They probably don't. But they do have lahar drills. And what happens is that you have sensors on the flanks of the mountains, on the rivers. If a lahar is coming to the town, then you're going to get the lahar warning. And what happens is that everybody in the school has to leave the school, and they have to climb up the hillsides on the side of the valley. You take everybody with you. If you have people with limited mobility and wheelchairs, whatever, you work to carry them. You get everybody up out of that valley and up onto the higher hillsides, and there's a time limit. They know roughly how long it would take for the lahar to get to them, and they practice getting everybody out of the school and up out of the way of the lahar in case it happens someday. Now, I want to point out that Tacoma, Washington is a pretty big city, and you see it up there in the top left of this map. And we looked at a picture of Tacoma. Remember Mount Rainier in the background, how big it looked? Parts of Tacoma are built on past lahar deposits. Okay, that's very disturbing, because if that part of the town was buried in a lahar in the past, it's probably just a matter of when, not if, it happens again. What we do have for Mount St. Helens is a map of destruction. Okay, so in the pink In the very center there is the eruptive dome. That's where your caldera is. Okay, in the light brown, almost orange, that's where your pyroclastic flow went. And notice, instead of being kind of in a circle around the mountain, it's mostly to the north because you lost the north flank of the mountain. So a lot of people got caught up in that and weren't expecting it and got killed. In the dark brown, you have some of your lahar deposits down there to the south. In the tan dotted pattern, that I believe is the North Fork of the Toutle River, and that's where you have mud and debris flow issues. Now, where it's just white and you have the arrows, that is the blast zone. And you might think, well, that's not so bad. They were out of the way of the pyroclastic cloud and they were out of the way of the lahar. How bad could it have been? Well, I'm going to show you how bad it could be on the next slide. But first, I'm just going to tell you that if you ever watch Discovery Channel, there are many 1-hour specials on Mount St. Helens, and my favorite ones are where they go and interview people that either observed the eruption from a safe distance or people that lived through it, telling their stories. And of course, sometimes they'll talk about the people that did not make it. And there was a young couple just out of high school that were camping on the North Fork of the Toutle River, and they were too far away to hear the sound of the eruption because sound waves dissipate quickly. They didn't know it happened, and they didn't know that the lahar was coming, and they got swept up in the lahar. And they managed to survive just barely. The guy managed to climb up on a log, and the girlfriend was on a log. Then she went under. He managed to find her and grab her and pull her up on the log. And they basically had to, kind of like a lumberjack, go from log to get themselves over to the shore. And they ended up living. They had all kinds of injuries, you know, broken ribs and things. And she spent some time in the hospital. But they both managed to live, and that's just incredibly amazing. Okay, so on the left is a nice sort of step-by-step. Time one, you know, hundreds of years ago, or well, we'll say 123 years prior to 1980, the magma chamber is not super full. But over the decades, that magma chamber gets really full. And then the magma is trying to bust its way out of the north flank, which is why you had a bulge in the north flank. And then there in time 3 on the bottom, well, you have your 5.1 earthquake, you have the north flank slide away. That's like shaking the pop bottle and then pulling the top. You have your vertical blast, you have your lateral blast out the north flank. Over on the top right is a nice photo of Mount St. Helens, and you see both the vertical and lateral parts of the pyroclastic cloud. The pyroclastic cloud is death. Nobody can survive that. What about the blast zone? Here it might not look that bad. This is the blast zone. Okay, so just the power of the blast and rushing air is horrible. So look at all those blown down trees. And if you look at the inset there, you might think that looks like some corn stalks, but that is what's left of what had been a nice, healthy, tall hardwood tree. And that's all that's left of it. And that's just from the blast. Okay, the lava didn't reach there, the pyroclastic cloud didn't reach there, the lahar didn't reach there, and yet it's still just utter devastation. Here's a close-up of that destroyed tree. So here's an image of the Mount St. Helens eruption from the air. You can see that scary pyroclastic cloud. You can see it kind of going to the north there. Here is just a different version of before and after of Mount St. Helens. This is a nice picture and drawing showing how tall Mount St. Helens was. And then there's a map in the top right just reminding you where Mount St. Helens is located, say relative to Mount Rainier or Seattle or Tacoma. And of course, this is afterwards. It just looks so different. In this image, I'm guessing some months have passed, maybe even a couple, 3 years. You've got vegetation growing back. You have the resurgent dome growing. Anyway, you lost a pretty big chunk of the mountain in that eruption. Here's an image of Mount St. Helens from a safe distance looking at that eruption. It almost looks like a nuclear blast. Okay, so this slide's kind of important, and I don't know if we'll have time to talk about it in class or not, but what's important here is this. This is a listing of all the volcanoes in the Cascades, okay? So this spans Northern California, Oregon, and into Washington. So the Cascades, remember, that's a mountain range, and it's there because you have a convergent boundary, right? Ocean to continent subduction zone. There's some review there. Not every mountain is a volcano, but several of them are. And these are all the volcanoes. This is where they are on the map. This is their name. And then we have an idea of how active or dormant they might be. So every one of these little volcano symbols represents from 1 to several dozen eruptions closely spaced in time. Okay, so my question to you might be this. Which of these volcanoes is the most active going back over the past 4,000 years? Is there a clear winner? Yes, there is. Mount St. Helens is the winner. Yes, Mount Shasta is very active. And then several of these have had relatively recent eruptions. Mount Shasta, Lassen Peak, Mount Hood, Mount Baker, Glacier Peak, even Mount Rainier had laharas due to heat loss in the 1800s, but Mount St. Helens is clearly the winner. Crater Lake is on here, also known as Mount Mazama. Don't forget, Crater Lake is actually a caldera. Notice it hasn't had an eruption in the past 4,000 years. That's because Mount Mazama erupted, I think it was 7,000 years ago when it formed that caldera that today is called Crater Lake. Okay, volcanic hazards. There are many volcanic hazards. Are you going to need to know these for your exam? Yes. I believe it's in the form of matching. Okay, so lava flows. Yes, they're a volcanic hazard. In your shield volcanoes, it's basalt. In your stratovolcanoes, it's andesite or rhyolite. Volcanic ash or volcanic hazards. Microscopic shards of volcanic glass. On one of the upcoming slides, you're going to see a scanning electron microscope image of volcanic ash. It looks like little razor blades of glass. So this forms ash flows and ash falls. So the volcanic ash is very hot. You don't want to breathe it in because it'll burn your lungs. It can also cut your lungs because it's shards of volcanic glass. The pyroclastic flow, also sometimes called pyroclastic cloud. This is, of course, that big, scary gray cloud. This is by far the most dangerous part of the eruption. It's an avalanche of pyroclastic debris. What's pyroclastic debris? Oh, we're going to get to that on an upcoming slide. These pyroclastic flows travel very fast. They can travel up to over 100 kilometers per hour. No, you cannot outrun that on foot. And then the French have a funny sounding name for this. They call it nuée ardente, which is French for glowing cloud, and that just simply means pyroclastic flow. So here are some images, a lava fountain on the left. There in the center, that's Paracutin down in Mexico, volcanic ash. Up in the top right, that's probably Big Island of Hawaii. Before the lava even gets to your house, it's going to go ahead and set it on fire. But of course, you had plenty of time to get out. And then in the bottom right, maybe that's one of the Caribbean islands, Montserrat or somewhere, where you've had lava flows come in and ruin a town. I don't know which volcano this is. I don't remember which textbook this came out of. It could be the textbook you're using now or a textbook we used to use. Anyway, this is just another image of that pyroclastic cloud. Okay, so volcanic ash, what does it look like? Okay, so that image on the bottom left that's what it looks like with the scanning electron microscope. Notice it looks like little razor blades made of volcanic glass. That's what's in the ash. So for many reasons, you would not want to breathe in volcanic ash. You just got to get out of the way. This is from Iceland. Okay, so Iceland, that's in the North Atlantic, and it's islands, and this is another hotspot volcano, mantle plume, in an oceanic setting. So it makes big shield volcanoes. Notice the dark material there. This is mafic. So this is your much less dangerous type of eruption, but it's still hazardous. Somebody used to live in this house, and then they had to evacuate when eruption was getting close, and they're never going to go live in that house again. You could skip this slide. Okay, this, I'm not sure which volcano this is. This could be Pinatubo or Montserrat. Anyway, just another image here of that scary pyroclastic flow coming at you. And you can't outrun them. I have one quick story of survival. And I forget where this volcano was. It was some island nation. It was an older couple, and they lived in the valley. And the volcano was one side, and then there was a ridgetop mountain on the other side. The kids were grown and gone, and they had like a Jeep 4-wheel drive type vehicle, and they didn't evacuate. And then the eruption happened, and the pyroclastic flow was coming down the mountain at them. So they got in the vehicle, and I guess the mountain on the other side had been clear cut to somewhat. They had a path, and they actually drove up the hillside on the other side. So they got themselves up high out of the valley, and they were able to avoid the pyroclastic flow, and they lived to tell their story on Discovery Channel. This is Mount Unzen, Japan, and just look at that scary fast pyroclastic cloud coming down. Can your car go fast enough to outrun this? I don't know. It's best not to even test that hypothesis. It's best to evacuate. It's possible that in these images that these last vehicles left are officials that have gone back in to make sure that everybody evacuated. More on pyroclastic debris. Okay, you can skip lapilli, but I would write down the other three, okay? So lapilli are fun. That's just a term for pea-sized rounded fragments of ash, pumice, or scoria. Lapilli is not on your exam. I might want you to know the term tephra. This is, again, a generic term for unconsolidated volcanic debris or fragments. Lava bombs, you do want to know that for your exam. Again, part of your volcanic hazards are in the form of matching. Lava bombs are blobs of lava that freeze in midair, as in they are ejected out of the volcano, molten lava. As they move up with the force of the blast and back down with gravity, they're going to solidify in that time frame and become this heavy lava bomb. Lava blocks are chunks of rock from the volcanic pipe or conduit that get chucked out of that pipe and thrown out of the volcano during an eruption. Over there on the left, we have a lava block. We have a geologist standing there for scale. It's taller than his knees, very heavy. Notice behind the scientist, there's a crater. This is an active volcano. There's steam and ash coming out of it. There's an image of tephra, lapilli. On the right, there's a dime for scale. Okay, lava bombs. The one in the top left looks kind of like a football shape. The one we have in class looks similar. They often kind of get that shape. The one on the top right is pretty big. You have some little scrub bushes there for scale. The volcano it came from is clearly in the background. But look at that image on the bottom left. Okay, that's a full-grown adult human. She's got to be at least 5'5". And then look at that lava bomb she's standing beside. It's much bigger and heavier than she is. And it was even bigger at the time it first fell. Clearly many pieces, exfoliation pieces have fallen off of it. Okay, more volcanic hazards. You're going to want to write all these down. Again, this is part of your matching. So the blast. The force of the blast itself can flatten the landscape, and we saw that with images after Mount St. Helens. So the blast of a volcanic eruption is similar to detonating probably more than one nuclear bomb at the surface. Just very explosive. Landslides. You can have landslides that happen in conjunction with your eruption. They might be caused by earthquakes that happen before the eruption. The landslide might be part of the eruption sequence, as was the case with Mount St. Helens. So earthquakes. We always see an increase in the magnitude and frequency of shallow earthquakes prior to eruptions. And this is very dangerous because it can trigger landslides. Before you even have the eruption, you can have tragedy. With landslides, it can collapse bridges and dams. And then tsunamis. We'll discuss tsunamis more after the third exam when we talk about earthquakes. The most devastating tsunamis are produced by earthquakes, but volcanic eruptions can produce tsunamis as well. So imagine your volcanic islands. Remember the volcanic island arcs? Like the Mariana Islands? If you have a big pyroclastic eruption at sea and you put a lot of volcanic material, pyroclastic material in the ocean quickly, that can trigger a tsunami. And then lahars. Just the first bullet here would be fine. I think this will tie up our volcanic hazards for the matching. Again, what are lahars? They are volcanic mud flows, and they're super dangerous. And this, of course, is because you have snow and ice that melt when that volcano erupts. These things are super deadly, and they travel very fast. So the pyroclastic flows, I believe, traveled at over 100 kilometers an hour. The lahars are slower, but 50 kilometers an hour. You can't just outrun that. And the Mount St. Helens lahar followed river channels, and it traveled over 40 kilometers from the volcano. So that story I told you about the young couple that just graduated high school and were out there camping, they were too far away to hear the sound of the eruption, but they were within the path of the lahar. Here are some images of the lahar. I wish we had video of the lahar from the 1980 eruption, but you know, things were different then. You guys, a lot of you weren't born yet. I was a kid, and we didn't have cell phones. So everybody didn't just have a cell phone with not only able to take pictures, but take video. Things just weren't like that back then, and we just don't have video of the lahar from the 1980 eruption. I wish we did. There's a picture, a static picture of it, and the pictures just don't do it justice. On the right there is a lahar in New Zealand, and whatever that metal structure is, the water's dumping it behind it, it's probably going to get knocked down by the lahar. This is a ski area in New Zealand. If you look closely, you can see the outline of the crater. So you don't see down in the crater because it's chock full of snow and ice. But you see all that dark, muddy looking stuff. What happened here is this is a small lahar, and you didn't have to have an eruption to produce this lahar. All you had to have was some heat loss. So clearly this is either a helicopter or an airplane, probably a helicopter, I guess. They're flying around the top. So the lahar warning must have been triggered, and before they could let anybody go ski, they're going to fly around up there and kind of check it out and see if things are safe enough or not to let people ski that day. So Mount Pelée is another famous eruption that you may or may not have heard of, and this happened back in 1902. And this was a town called St. Pierre on the island of Martinique. This is in the Caribbean. The Caribbean is a dangerous place to live, by the way. And on the right, you see a very nice coastal fishing town. I mean, it's 1902. You don't have YouTube or MTV or cell phones, or really any TV. But, I mean, life probably wasn't horrible. I mean, hey, you lived on the coast. Maybe you had a fun school to go to. And then over on the left, we see our sad boy sitting here. And hopefully everybody, you know, evacuated and escaped. But now he's looking down on what had been a very pretty town. And now it is in ruins. Volcanic hazards. Lake Nyos. You are going to need to know something about Lake Nyos for your exam. So I might write down that last bullet there. Okay, so this goes back to our volatiles, volcanic gases. They can cause tragedy even if you don't have an eruption. And our sad example here is Lake Nyos. This is in Cameroon, Africa. Africa has 5 hot spots. North America only has 1 that we know of. We don't know of any in Eurasia. There's probably hot spots in Eurasia that we just haven't made to the surface yet. But Africa has more than its fair share. It's got 5. So Lake Nyos, this is a volcanic lake, perhaps a caldera. And it's, of course, it's where you have a hot spot, where you have a mantle plume. So unknown to the locals, unfortunately, there was a dangerous buildup of carbon dioxide gas accumulating in the sediments and the bottom waters of that lake. And of course, where was that carbon dioxide coming from? From the magma chamber, not too far away, because this is a mantle plume hotspot volcano. This is back in 1986. So somebody had left the village to, you know, whatever, to go to another village, visit family and friends, go conduct business, whatever. And they came back and everybody was dead. So about 1,700 people that were living there, they were all dead. The animals were dead. And there were no obvious signs of trauma. And so, of course, this person's figuring, what in the world's going on? This is horrible. What could have happened? So this person must have gone back to the other town and alerted authorities, and the word gets out, including to scientists across the globe. So scientists from different countries came in and investigated. And what they discovered was evidence for a landslide. So what must have happened is that a landslide disturbed the sediments on the lake bottom. By the way, you could write down the last two bullets here, I think would be good. So this landslide must have, sent debris to the bottom of the lake quickly. And basically it released this big bubble of carbon dioxide gas. This was very unfortunate. So carbon dioxide, can we breathe carbon dioxide and live? Well, no, we have to have air, nitrogen and oxygen. And we expel carbon dioxide. And if we're trapped in carbon dioxide for too many minutes, well, we will die from that. So if you look at the periodic table of elements, you'll see that carbon dioxide is more dense than air. So you release all this carbon dioxide and it basically flooded the landscape and it pushed the breathable air up higher. And nobody could escape it. They probably didn't even really know what was happening or realize it. Carbon dioxide doesn't have a smell to it, so they probably really didn't even know what was happening to them, and then they just keeled over. I would write down how about bullets 1 and 2? Yeah, so as we said on the last slide, unfortunately, carbon dioxide is more dense than air, and it surrounded the countryside, and it killed everybody in the path and all the animals, farm animals, birds, if they had cats and dogs, everything was just dead. So steps have been taken to try and keep this from happening in the future. There are now wells installed, as in they're drilled down into the bottom waters of the lake and into the sediments, and then you get them going with a pump, and then it's kind of like an artesian well. So what happens is that you have carbon dioxide continuously being vented from the bottom of the lake. And of course the idea here is that hopefully we're not going to have that dangerous buildup in the future ever again. And can we be around a little bit of carbon dioxide? Yeah, we're around it right now. When we are in the classroom together, even when there's only half of us there, we're all breathing out carbon dioxide, but we're doing fine because you have lots of ventilation and lots of air. So that's what they're doing to try to keep this from happening again in the future. This is an image of Lake Nyos. I'm assuming not too many days after what happened. You see that the water's very dirty looking. It's been churned up, and of course this was further evidence that a landslide had happened. So the drawing on the left is showing setting up these kind of self-running wells that'll vent the carbon dioxide safely to the surface. And then that photo on the right is one of these floating platforms where they're doing that. So, yes, they're shooting water up into the sky as well. You're bringing that water with the carbon dioxide in it up from the lake bottoms, so that next time you have a small earthquake, because we assume that's what caused a landslide, next time you have a small earthquake and a landslide, that you're not going to release carbon dioxide and kill anybody. Okay, question here. What famous disaster was caused by a stratovolcano? Well, Vesuvius, which we have mentioned before. So again, back in 79 AD, Mount Vesuvius erupted. It buried the towns of Pompeii and Herculaneum in the red dashed lines. That's the outline of the modern city of Naples. So the people living in Naples are potentially in danger in the future. I have to admit that Naples and Vesuvius are pretty high on my bucket list of places to visit. On the bottom left there, you see casts of the victims. So what happened here is that, why did these people not leave? Okay, well, this was a different time. Would there have been signs? Yes, there would have been earthquakes. There would have been smoke and ash coming out of the top of the mountain. All kinds of scary signs. They probably just thought that the gods had been angered, and it didn't occur to them that it was Mother Nature and that they should leave. So most people were there when the eruption happened, and there was nowhere to go. They couldn't go anywhere. They couldn't move fast enough. So their bodies got encased in the ash, and then the bodies burned away, and then the ash outlines of the bodies are left. You don't need to write any of this down, but yeah, so mid-1700s, mid-18th century is when they discovered Vesuvius and they began to excavate it. And Vesuvius, well, they refer to this particular type of pyroclastic eruption as a Plinian-style eruption. And that description also goes for Mount St. Helens eruption in 1980 and Mount Pinatubo, which was back in about 91, 92, I believe. So where's Mount Vesuvius? There it is. So this is Italy, and the Alps are there between Italy and the rest of Europe because a microcontinent that contained what is now Italy crashed into the Eurasian plate, making the Alps. Anyway, so you see there where Vesuvius is located, and there's another dangerous active volcano not too far away called Campi Flegrei that not everybody's heard of. Stromboli. It's not just a delicious calzone-like thing that you can order at the Italian restaurant. It's also an active volcano. And then there's Mount Etna on the island of Sicily. Mount Etna is actually a well-behaved volcano. I would not be nervous to live near Mount Etna, not at all. But I would be a little nervous to live near Vesuvius. So here are some more images from Vesuvius. So Vesuvius is very active. It had a much smaller eruption back in 1944 in World War II. What was it about 44? World War II was going on. Paracutin grew out of a farm field in Mexico, and Vesuvius had a small eruption. Anyway, there's a picture of a small pyroclastic eruption. And then there on the right are the casts of victims again. Volcanoes and climate. What you're going to need to know about volcanoes and climates. Yes, how about bullets 1 and 4? Yeah, bullets 1 and 4, the first and last bullet. That's really all you have to write down. But I am going to want you to know something about volcanoes and climate. So can volcanoes affect climate in the short run? And the answer is yes. Okay, how does this happen? And it does not always happen. Okay, some large volcanic eruptions, pyroclastic eruptions, occasionally even shield volcano eruptions, can spew ash all the way up into the stratosphere. So we live in the troposphere, the lowest layer of the atmosphere. That's where the weather occurs. And the troposphere goes to about 7 miles up. The stratosphere is above the troposphere, and it's above the weather. So sometimes some of our large volcanic eruptions will send ash all the way into the stratosphere. And why does that matter? Well, it's above the weather, therefore it's not going to just come back down with the next rain. And it's going to encircle the entire globe in about 2 weeks, and then it's everybody's volcano. And because its particles are so tiny, they're going to take a very long time to settle down to the surface. So ash may stay in the stratosphere for several months or a few years. And what does this ash do? It blocks incoming solar radiation and causes a global temperature drop. Do we have examples? We do. I'm going to want you to be able to give me an example of a volcano that affected climate. You could choose to tell me about any of these, and maybe there's some others as well. Okay, so 1815, Mount Tambora in Indonesia had a huge eruption. 1816 is known as the year without a summer in Europe because that ash went into the stratosphere, and they had crop failures. Like their summer didn't act much like a summer. It was colder than it should have been. 1883, Krakatoa, which they say was the loudest sound modern humans have ever heard. Estimated global temperature drop of 1.2 degrees Celsius. Mount Pinatubo in the Philippines, 91, cooling of 0.3 to 0.4 degrees Celsius. Even Mount St. Helens, which was not a huge eruption by any means, although it was a big deal for Americans. We had a 0.1 0.1 degrees Celsius decrease, and that C should be capitalized. That's a typo. There are some older ones here, like Laki, Iceland, 1783. So we could say we didn't necessarily have very modern science at the time. Science was still kind of rudimentary. But the average winter temperature in New England in 1783 dropped by like 4.8 degrees Celsius. Okay, that's a huge difference, and people noticed it. All right. And Ben Franklin, he was already famous at that point, and people listened to what he had to say. He may not have been the only person to hypothesize that these two things went together, but he is credited with figuring out that, once he heard about this big eruption of a shield volcano in Iceland, and they had a very cold winter, he hypothesized that the eruption had something to do with it. And he was correct. And how about Yellowstone? 640,000 years ago. Yellowstone, supermassive eruption. Would that have changed climate around the globe for some number of years? Yes, absolutely. Okay, next topic. So we're getting close to the end. Maybe this will only be a 2-hour and 15-minute PowerPoint. We'll see. Okay, so when geologists, the study of volcanoes, are known as volcanologists, what do they look for on particular volcanoes? What kind of activity are they looking for when they're trying to predict an eruption? Okay, so earthquake activity. The most reliable precursor is an increase in the frequency and magnitude of shallow earthquakes. Did we see that with the Mount St. Helens? Yes. Heat flow. We're going to measure heat flow coming from the rock. If you have more heat coming out of that rock than you did when you checked last year, well, guess what? That magma's probably close to the surface. And maybe it's going to erupt soon. Hot springs. If you have increased temperatures of hot springs, then that also might tell you magma's getting closer to the surface. So when do you start looking at this stuff? Do you wait until you start to see activity to take measurements? No, it's too late then. You have to have scientists going to these active volcanoes from time to time and taking measurements. You need to know what the background temperature of that hot spring is so you can tell whether or not it has increased. Changes in shape of the volcano. You have a bulge on the north flank like Mount St. Helens. Well, we learned a lot then. That definitely tells you that the volcano is going to erupt and that you might lose that side of the mountain. And how do we look for changes in shape? Well, we still do use these old school things called tilt meters. Of course, these days GPS is pretty good, and laser surveying. We also look for new fractures. We might go out and map new fractures. And do we see these things in Mount St. Helens? Yes, we saw fractures at the summit and the bulge on the north flank. Gas emissions. You need to know what your background levels of gases are coming out of that volcano so you can know when it has increased. We don't watch Dante's Peak anymore. We haven't for a long time, and we certainly wouldn't do it with COVID. But what I will tell you is this. Whether you have cable, Netflix, YouTube, Hulu, whatever TV thing you have, if you can watch Dante's Peak sometime, I highly recommend doing it. Yes, it's Hollywood, but it's, in my opinion, the best volcano movie. And there's a quick story there. So the guy that was the producer for Dante's Peak, when he was first in college, he was a geology major. But then he took a filmmaking class and he changed his major. But he never forgot geology. And he always said that if he ever had enough influence over a studio to convince them to do a movie about a volcanic eruption, that he was going to do it. And he did finally convince the studio, and they made the movie Dante's Peak. It came out, I don't know, 95, 97, something like that. It's a great movie. You should watch it. So just some images here. On the far left, that's laser surveying, looking for changes in topography. Bottom left, that's an old-fashioned tilt meter. If it tilts, then we can measure that and know that the ground is deforming. Bottom right, that's using some false color satellite images to detect heat. And believe it or not, the blue there is representing heat coming out of that very active volcano. That's Augustine Volcano in the Alaskan, the Aleutian Islands in Alaska, very active. And then on the top, that machine there is a gas chromatograph. And from a halfway safe distance, you can set up that machine and read the gases coming off it. And then back at the top left, of course, the increase in magnitude and frequency of shallow earthquakes is your most reliable precursor to an eruption. What can you do about volcanoes? Can you stop them from erupting? No. And believe it or not, a tectonically dead planet is not a planet that can host life. So it's just as well that our planet is alive and not tectonically dead like Mars. Do we have life here? Yes. Do we have life on Mars? Not that we've ever discovered yet. So it's kind of okay that we're tectonically active. We can't stop the volcanoes. Can we do anything about them? Yes. The one thing we can do that's not actually listed here, but we just discussed, is that we can monitor the volcanoes. You gotta pay scientists, you gotta have a USGS program, and that some people, that's their job. I think that would be a fun job, to go out to the volcanoes from time to time and gather readings on things. Okay, but what else can you do then? Well, is this potentially on your exam? Yes. We can create hazard maps, danger maps, like you have here with Mount Rainier. You can make evacuation plans. And when should you make evacuation plans? Should you wait until your volcano is angry to make evacuation plans? No, you need to have them in plan or in place, long before, and maybe practice from time to time. And then, of course, you might be able to divert lava flows, which sounds weird. But if it's a volcano that is either a shield volcano or acts like a shield volcano, you might be able to do that. So this happened in Iceland back in 1973, and Mount Etna during World War II, 1944, but also again in 1983 and also again in 1992. We'll talk more about that on an upcoming picture. This is Iceland in 1973. Remember, this is a volcanic island in the middle of the North Atlantic. It's there because you have a mantle plume. It's shield volcanoes. Notice the basalt. But it's still hazardous because there was lava flows, and the lava flows were getting dangerously close to one of the ports. And Iceland relies on fishing quite a lot, so they couldn't let lava overtake this port. So somebody came up with a crazy idea that we'll hook a bunch of pipes and hoses together, and we're going to pump cold seawater onto the advancing lava to harden it and kind of make it form walls. Basically, they were building levees to divert the lava away from the harbor, and guess what? They were successful. Did they stop the lava from coming? No, but they were able to tell it where to go. Okay, recurrence interval, I think, is not on your exam. We'll very briefly discuss it. And there's no real good cutoffs here. Okay, so a volcano is active if it has erupted recently. What does recently mean? Within hundreds of years to thousands of years. And if we think it's likely to erupt again soon. Mount St. Helens, Mount Rainier, Mount Baker, Lassen Peak, things like that. Okay, dormant. It's dormant if it has not erupted for, say, hundreds to thousands of years, but could potentially erupt again in the future. I would say Mount Mazama, where Crater Lake is, that's a caldera, that's probably dormant. It erupted about 7,000 years ago, but there is still a subduction zone offshore, so it could erupt again in the future. And we're not going to call that volcano extinct until it's no longer in a tectonic setting to generate partial magma, no threat of future eruptions. What's a great example of an extinct volcano? Diamond Head on the island of Oahu. Remember, that island has moved off the hot spot, so it's not being fed magma anymore, and we could say that Diamond Head is extinct. So here's just a map of some famous volcanoes. You can pause here and look at this if you would like to. Volcanoes and plate boundaries. I will put something regarding this on the board in class together, or a video lesson. I'd say, which ones am I going to ask you on the exam? I would write down the first bullet and the third bullet, so you can skip the second one. Okay, so volcanoes and plate boundaries. So oceanic hotspots. In other words, a mantle plume in an oceanic setting, like the Hawaiian Islands or Iceland. What kind of volcanoes will you get? Every time, shield volcanoes. Continental hotspots, you don't need to know for your exam. We'll briefly discuss it. In the early stages, you might get flood basalts, like we had in India that killed the dinosaurs, or in Siberia that caused the Permian mass extinction. And then later on, it might lead to pyroclastic style super eruptions like Yellowstone. Okay, third bullet, mid-ocean ridges. We already know this, but you should write it down. Remember that mid-ocean ridges are underwater volcanic mountain chains, and it's gentle volcanism producing basalt. Effusive eruptions. Okay, yes, don't forget that Iceland is a hot spot on a mid-ocean ridge, and that image to the bottom right, that's an awesome image of where somebody's built a house just a little too close to the shield volcano. That might be the same house with the same blue roof that we saw in a previous image where you had all kinds of eruptive material on top. Clearly, the people have evacuated this house at this point. I would write down both of these bullets here, and we will discuss this in class together. So we're still on this topic of volcanoes and plate boundaries. So what about the subduction zones of the world? Well, both your ocean-to-ocean subduction zone and your ocean-to-continent subduction zones are going to give you pyroclastic eruptions and stratovolcanoes. All right. You can leave out anything that's in parentheses here as you're writing these down. Okay. Oh, and how about some review here? Your ocean-to-ocean subduction zone gave you volcanic island arcs, like the Mariana Islands. They're going to give you stratovolcanoes, pyroclastic eruptions. Your ocean-to-continent subduction zones are going to give you continental volcanic arcs. That's not written down, but I'm just saying it to remind you. And of course, we'll also give you pyroclastic eruptions and stratovolcanoes. So the subduction zones of the planet are always going to give you stratovolcanoes, very dangerous eruptions. Here is a slide just kind of trying to tie together different plate boundaries and different types of volcanoes that you're going to get. Here is another image of an ocean subduction zone creating stratovolcanoes. And in this particular case, we're looking at Mount Augustine, a very active volcano. Oh, I'm sorry, this is ocean-to-ocean subduction zone, yes. And you're looking at the Aleutian Islands here. Another famous volcano back in the 90s. So this is Montserrat, which I believe is in the Caribbean. And they had to evacuate people from this island. I think they evacuated the entire island because this very dangerous volcano, Soufriere Hills volcano, erupted between 95 and 97. And they've had some milder eruptions since then. Including this particular image was taken in 2009, and you see over there on the left pyroclastic flow and lahar deposits from the eruptions in the 90s, but clearly it's still active. I don't know if anybody still lives on Montserrat. Maybe there's a handful of people down there to the southeast that are able to live there. And here is a drawing of the ocean-to-continent subduction zone. So a little bit of review here. Remember that this could represent the Pacific Northwest and the Cascades and Mount St. Helens and Mount Rainier. And then this is a slide here from one version of your textbook that trying to tie together the different plate boundaries and the types of volcanoes present. I believe this is our last topic. Are volcanoes beneficial at all? Well, yes, they are. We spent 2 hours talking about how dangerous volcanoes are. But guess what? Volcanoes also have some positive aspects to them. Okay, so they can be beneficial. Might I ask you this on the exam? Sure. I might ask you to give me a couple, 3 examples. So let's go through these. Volcanic outgassing early in Earth's history created our atmosphere that we breathe and our surface water. Volcanic soil is very fertile. It's great for agriculture. It gives you good nutrients that you need. So granite, for example, good volcanic soil, but particularly the extrusive kind. So soil made from basalt, andesite, or rhyolite. Third bullet there, volcanic eruptions and intrusions early in Earth's history created the crust and continents that we live on. Other reasons why volcanoes are beneficial. Well, we need precious metals. They're very useful in our electronics. And precious metals are formed and sort of aggregated, or they're in concentrations that make them economically viable to go and get. And this happens as a result of volcanic activity, magma chambers, and hydrothermal activity. Geothermal energy. So Iceland does not import coal from West Virginia or Kentucky and burn it and pollute the countryside. They don't need to. They have all the free geothermal energy they could ever want. Diamonds. If you don't care at all about jewelry, that's okay. Everybody makes use of diamonds because diamonds make good cutting tools. And many of the products that you might have in normal society were shaped by diamonds, and they were formed in subduction zones, a type of convergent plate boundary brought to or near Earth's surface in these things called kimberlite pipes, which are very deep-seated, now extinct volcanic conduits. And lastly, scientists believe that life may have begun in the vicinity of black smokers, which are volcanic vents, gas vents at the mid-ocean ridges. So it's possible that the moon was tectonically active in the past, although the basalt flows, we do believe, in general, those have come from melting from meteorite impacts. I think this is our last slide. Okay, so over on the right, that's a satellite or space telescope image of Olympus Mons, which again is our largest volcano in the solar system. And it's a shield volcano, and it's on Mars, and it's extinct. So Mars used to have internal heat. It does not appear to have any internal heat anymore. Did it have actual plate tectonics and plate boundaries? Not sure, but it did have active volcanoes in the past, and there is wind on Mars. We know that. There is, we know that we have frozen carbon dioxide ice on Mars, and I believe they found evidence for frozen water ice on Mars at the poles in the wintertime. And then over on the left, you have a volcano on Io, one of the moons of Jupiter. And that's it.